This is an inverting op amp, and it's going to look like this. This is ground, and I think I'm going to move this over a little bit. This is my V out. This is my R2, and that is 22K. This is my R in, or R1, and that is 47K. And my V in here is going to be 3.2, so positive 3.2 volts. Okay, and so what we need to do is calculate all voltage and current values. All right, so first things first is the first golden rule of op amps is that we match the inputs. And what does that mean? That means we're saying, oh, this should be minus. We're saying that V plus or V non-inverting is equal to V minus inverting. And the next thing we're going to do is we're going to say no current into the inputs for Kirchhoff's current law. Okay, so what we're going to start with is we're going to start right here. So I've got right here and here, we're going to match these voltage values by number 1 here. So we're going to say that our, let's call this point A. So this is point A. All along here is at voltage, at the same voltages as at A. So we're going to say VA is equal to V plus right here, and that's equal to 0. And so the next thing we can do then is we can find the, so if I look, just erase this a little bit, write that over here, 3.2 volts. So if I look here, my voltage here is 3.2 volts, and what I need to do is find the current, and it's going this way. So if my voltage is 3 volts here, and my voltage is 0 volts here, then my current has to flow from left to right. So that's going to be my I. And I can find that current because I can say that my voltage drop, so V drop across R1 is equal to the voltage at is 3.2 volts, my source voltage, minus V at A divided by R1. And that's going to be 3.2 volts minus 0 over R1 is 47K. So let's just pull out my MATLAB. MATLAB doesn't like rotation, so oh, come on, MATLAB. Okay, so 3.2 divided by 47,000 is equal to, so that's 68 microamps. Go back. Oh, and yeah, so this should be my current here. So let me erase this. This is not a voltage, it's a current. So this is my voltage drop across R1, 3.2 volts minus VA. My current is through R1, we'll call it I1, is the voltage drop 3.2 minus VA over R1, and we found out that is I1 is equal to 68 microamps. Okay, so if we know that the current here is 68 microamps, and we know that no current goes here, so we know I equals 0 here, then we see that this I1 is equal to I going into the minus plus I going into R2. And since this is 0, we know I1 is equal to I2. So this is my I1 also, since they're equal. So we can calculate the, if we know that the voltage at A is 0, and we know the current through our R2, then we can find out the voltage at V out. So I'm saying that voltage at A is 0, and then I'm going to say minus I1 R2 is equal to V out. Okay, so V out is equal to VA plus I2 R2, or sorry, it should be minus that. VA minus I2 R2. So we know that the current is moving to the left. So if our current is moving to the from here, if it's moving left here, and we know it's moving left here, then we know we're dropping voltage in the direction of the current. So that's why it's got to be a minus. So V out then is 0 minus 68 microamps times 22K. And going back to MATLAB. Okay, so I can take the answer, so that I've already solved for 68 microamps. So I'm going to take that answer times 22K, and I get 1.49, so 1.5. So when I go back to here, I'm going to get V out is equal to a negative 1.5 volts. So in that case, I've calculated the current through and the voltage values at each point and the voltages across each of the resistors.